with chaos. I took this opportunity to really learn things, or try to learn other things I've really I've grown affinity to the studio, especially the more I've digitized myself, the more I've really come into the knowledge of simulation, and I really want to expand that. And that essentially really starts with thinking about chaotic behavior and the study of dynamical systems. So it's not really chaos theory in the sense that the physics sense, where everything can happen and does happen, but more on the ideas that systems can be deterministic, meaning the future conditions is fully determined by the initial condition. The process and evolution of it is really hard to determine. No random elements are involved, therefore that's why it is deterministic, and it's usually referred to as deterministic chaos. Very commonly observed in elements such as weather, because systems are based on predictions of current events, and that's why the weatherman always tells you to check the weather frequently and often. And all of this is really running on the idea of a simulation, which is the imitation or the operation of a real-world process. Something to really point out is the difference between emulation and simulation, which is emulation is really an ambition to surpass and to make it better. And when we talk about simulation, we really actually have to go to the root of simulation, which is the development of the computer for the calculation from the Manhattan Project, for just calculating the trajectory of missiles, more specifically nuclear missiles, in the early 50s and 60s. Simulation has essentially had a symbiotic relationship with the computer, and they've kind of grown together. So early simulation really leads to Conway's Game of Life, which is a cellular automaton devised by mathematician John Conway in the 1970s. It's considered a zero-player game. Its evolution is determined by its initial state, requiring no further input. Played by creating an initial configuration and observing how it evolves. It's an infinite two-dimensional orthogonal grid, a grid of square cells, each of which is either on or off. Its interactions only based between its surrounding 8 neighbors. Births and deaths occur simultaneously. Rules are applied continuously and create further generations. So there are 4 simple rules that govern the Game of Life. Pretty simple. Any life cell with fewer than 2 life neighbors dies, as if caused by underpopulation. Any life cell with 2 or 3 life neighbors lives on to the next generation, and any life cell more than 3 neighbors dies, as if by overcrowding. And ultimately, rule number 4, any dead cell with exactly 3 life neighbors becomes a life cell, as if by reproduction. There are certain patterns that are derived through seeing the simulation evolve. Some of them are static, and others are very active and just have oscillations or cycles that pertain. Some of them are very difficult to recreate, but most of them were actually visible at the initial demonstration. Let's start to talk about distribution of resources on a very cellular and basic level. We can usually describe as bacteria or other simple forms of life. And this really opened up the niche, which is called cellular automata, which is a discrete model studying computational theory, mathematics, physics, and complexity science. Essentially pertains to the same structure as Conway's Game of Life, based on on-off states on a grid, but the rules that govern the on and off states of the squares varies and alters. So here we have an example of that very same system, where right now we have logic being applied sequentially from top to bottom, and the cells are being turned on or off based on certain rules. The rules are alternating, so every time the sequence is over, a new set of rules is applied. So what we have here is another simple cellular automata simulation, which is, this one's based on avoidance. So each cell that's turned on is trying to avoid the next one, and really after time you start to see it create these lines as they're all above each other. It's actually more visible when you change the dimensions because it happens more rapidly. You can see the cells trying to avoid each other. And these behaviors actually start to get very complex, and they're usually more visible when you speed up the process. And this really starts to talk about adding more intelligence to the script. Adding more intelligence, really starts about adding more layers of behavior and code to the simulations, and really opens the new, that is the next phase of computational exploration, which was flocking behavior. So flocking works on only three principles. It's quite easily to emulate and simulate. Actually, it's three principles are cohesion, alignment, and separation. Cohesion represents the population, the sample population's mutual attraction to each other, as in safety in numbers. Separation represents a certain distance required to maneuver in order to avoid collision, and then alignment really specifies the ability or the need to move as a unit in order in direction, speed, and objective. So here we have one-to-one representation, or one-to-one within the screen of how the interactions will happen. So we have cohesion as the area that presents a mutual attraction between all the particles. And then we have alignment, which is how they want to come together and move together as a flock. And we have separation, that is essentially collision detection. So here we have the simulation, left top corner of the screen, and you can see I'm playing with certain levers and parameters, modifying the range of interaction of those three forces, essentially cohesion, alignment, separation, and depending on these, the calibrating or the fine-tuning of these three rules, you can really start to get complex behavior. To really be discussed is the critical mass, which is a certain size needed to require a specific result or action. If you only have a couple of particles interacting with each other, then you have very contrived movement. But if you have a large number, you really the simulation really gets a mind of its own, and it starts to mimic behavior that is really difficult to predict. It goes back to the initial start of the presentation, which was chaotic behavior, where each step can be calculated, but the end result is bottom-up, emergent. There's no real prediction to what the result could actually be. So this behavior modeling, it's really considered complex, and actually the term for it's emergent, because the complex system and patterns that arise out of it, out of the multiplicity of simple interactions, really produce a movement that is indivisible to an individual. They really move as a unit, bottom up, and hard to predict and to emulate any other way besides the simple interactions between each member of the population. And a very good example is this iteration here by Jose Sanchez, which is a modification of a flocking script. Jose Sanchez's simulation is a very good example of calibrating the script to really derive unconventional organizational outcomes. Something that he's been really working towards or working for is understanding these concepts and organizational behaviors and applying them to architecture, and that really brings up his his work, which is part of BioThing. We specialize in competition-driven design through simple simulations. They're a very good example of trying to mediate these processes into their design and use them as a form driver, as a big element of their design process. So in this example, we have an idea about cellular automata. Very much similar to the spore example at the beginning, where these cells or these particles are moving across a grid, and they're trying to avoid each other, and as they're moving across, they're shifting, manipulating a frame either one way or another, making these openings for a facade system. The outcome is not necessarily that appealing, at least personally to me, but the attempt to start to use this to generate a facade is an interesting procedure, and definitely an exercise worthwhile. But you can see its better application when you talk about different forms of form finding. For instance, in this example, where for their competition they use essentially attractor and repulsion points, very similar to magnetic fields, to start to derive not only the organizational element for the project, but structural elements, but also about the idea of how to attract people to certain points, and how the idea of pooling and the actual attraction that this waterfront project is trying to do. Once again, the simulation is controlled by a lot of parameters, most of them really difficult for us to comprehend at this point, but you can see that everything is essentially attached to a lever on the left side of the simulation, and it's really about optimizing, calibrating it to work. This doesn't really give you the greatest output, but it gives you the ability to generate your form finding or your form, and then go back and model the rest of the necessary elements for the project. So the simulation really stands as a generator of form, but not only form, but of logic and concept. The simulation takes a very early stage in the design process, and the forms that derive are once again unpredictable and very bottom up, based on relationships as opposed to defined geometries. BioThing hasn't really built too much, but they've really been exploring this idea, and they do teach prestigious schools, Columbia and AA and Pratt, but they haven't really found a way to make this mainstream, but they're definitely working towards that. And this really brings up a very important point about simulation. If we go back to the original simulation, or the original eye-opener simulation, which was Conway's Game of Life, when Conway was first investigating how various starting conditions could be developed, he tracked it by hand using the Go board with its black and white stones. This was very tedious and prone to errors, and was later made into a program by John Francis. But what's really what simulation has really done is provide this as absolute execution of logic that you can apply to design, and that's why it's really gained a lot of traction, because instead of really moving around geometry, you're moving around logic and thinking about how to manipulate form in a more generative process as opposed to a more direct process. So you talk about logic and its organizational elements as opposed to its aesthetic components, and then once you have derived this this formula of finding the fitness of form to the programmatic requirements, you're arrived at an architecture that possesses a lot of the pure logic and a lot of the integration to its surrounding that is present in a lot of natural systems.